Hello everyone, welcome to the fifth lecture of this module 4 where we are discussing interface circuit of microsensors and nanosensors. In today's class, we are going to discuss mostly on excitation circuits and some ADC and DACs because they are crucial part of a integrated circuit system or integrated sensor system. So let us learn what is excitation circuit, and origin of this excitation circuit lies in our first module where we have discussed the active sensors. So all active sensors actually require an external power supply. If you remember, we have defined two types of sensors, active sensors and passive sensors based on power supply. So active sensors require an external power source for their operation, maybe in nanowatt or in microwatt, doesn't matter, but if it requires, it's a active sensor. Power can be delivered to a sensor in different forms. It can be through a constant voltage source, or it can be through a constant current source, or sometimes some of the sensors require sinusoidal current or pulsating current kind of thing. Okay, let's learn one of the supply, which is current generator. Similarly, you can understand other excitation circuits also. So a current generator, sometimes also known as current pump, is a device or a circuit system which produce electric current which is independent of the load impedance, because we are not aware that what kind of sensor is going to be attached with the excitation circuit. Okay, so mostly the current generators are devices which can produce currents which are actually independent of the load impedance, and when I say load, I mean to say the input impedance of the sensor. Okay, so ideal current source or ideal current generator has basically infinite high output impedance. Okay, so any series load will not change anything in the circuit. Okay, so if the output of this output impedance is very high, whatever you are giving at the load is actually doesn't matter. Okay, there are two main characteristics of a current generator. They are output resistance of the current generator and a voltage compliance. As we have discussed just now, that the output resistance of this current generators should be very high, in fact as high as practically possible. Okay, and second thing, which is a new term in this course, that is voltage compliance. Okay, so voltage compliance is nothing but the highest voltage that can be developed across the load without affecting the output current. So you are not touching the output current at all, but you are actually tuning the voltage. So highest voltage that can be developed across the load without affecting the output current. Okay, so let us understand this in terms of one example. So if the required excitation current in a circuit or for the sensor is say 10 milliamp, and highest load impedance at any given frequency is say 10 kilo ohm, then a voltage compliance of say I into Z, where 10 milliamp is the current and 10 kilo ohm is the load impedance. So I into ZL, it's basically 100 volt would be needed. So that is the voltage compliance required. So if you have load impedance of 10 kilo ohm and excitation current required 10 milliamp, the voltage compliance is nothing but current multiplied by the load impedance. Okay, so here it is 10 milliamp and 10 kilo ohm, so it's basically 100 volt compliance is required. Okay, so mostly we require a unipolar current generators. So a unipolar current generators can act both as a current source and as a current sink. When I say current source, I mean to say that current is generated and it is outflowing, while a current sink generates the inflowing current. Okay, here unipolar, in this term unipolar current generator means that the system can produce current flowing in only one direction, and that direction is mostly to the ground. So unipolar current generators do produce current, okay, but that current is a unidirectional current, or mostly this current is in the direction of the ground. Okay, many of these generators utilize current to voltage characteristic of the transistors. Okay, now a voltage controlled current source or sink which is containing op amp is shown over here. Okay, if you see this circuit carefully, you have a precise and stable resistor R1 that defines the output current flowing through the transistor. Okay, the circuit also contains a feedback loop which is connected through the op-amp. I am talking about this feedback. Okay, so it keeps the voltage across the resistor R1 constant, and therefore the current is also constant. Okay, to deliver a higher current at a maximum voltage compliance, a voltage drop across the sensing resistor R1 should be as small as possible. So let me call it, say, VR1. Okay, so this VR1 should be as small as possible. Okay, the current I out can be simply this V1 or VR1 divided by R1, right? The current through the base of the output transistor should be minimized for a better performance. Okay, a field effect rather than a bipolar transistor is mostly used as an output current delivering device. Usually we avoid a BJT in this circuit because BJT has higher IB as compared to the input current in the FETs. Okay, so that is a little bit about excitation circuits. Similarly, you can also read about voltage generators, a constant voltage generators, okay, and other sources like pulsating current or pulsating voltage generators. Okay, now there is an important terminology you might have come across, which is ADCs and DACs, or analog to digital converters or digital to analog converter. So let us learn first about analog to digital converter in brief, and then we will see digital to analog converters. They are very essential circuit element in a interface circuit of a microsensor and a nanosensor. Okay, so AD and DA converters relates analog quantities to digital quantities and vice versa through an appropriate code. Okay, the most commonly used code is the binary code, in which the number is represented. You know that in binary you represent any number by different weights, multiply by 2 to the power n, n minus 1, and so on. Okay, so here one of the codes is written where this n is equal to dn into 2 power n plus d n minus 1 into 2 power n minus 1 and till d0 into 2 to the power 0. Where these coefficients dn minus 1, d2, d1, d0, they are assumed value of 0 or 1. The leftmost bit is this dn into 2 to the power n. Okay, so as I have mentioned that this dn or any d1, d2, anything can be either 0 or 1. So this dn to the power n is called the MSB or most significant bit, and that it has a weight which is maximum, which is in fact twice as large as the next most significant bit, right? So this is evident as 2 to the power n has twice as large weight as 2 to the power n minus 1. Okay, each binary bit has a weight that is twice of the weight of the next less significant bit, and the least significant bit, which is also called LSB, is on the extreme right of the binary. Okay, so the full scale output voltage of a n-bit converter can be given as E naught is equal to ER into the code, right? D n minus 1 into 2 minus 1 plus d n minus 2 into 10 power minus 2 and plus d1 into 2 power minus n minus 1 plus d naught into 2 power minus n, where ER can be any convenient reference analog value required in that particular circuit. Okay, therefore there is a difference between E naught and ER, hence there is a error, and this difference E naught and ER in this E naught and ER, okay, decreases as the number of bit increases. Okay, and the resolution of this kind of device is nothing but the full scale deflection divided by 2 to the power n. Okay, and similarly the dynamic range can be calculated as 6 into number of bits. Okay, so let us learn some digital to analog converter circuits, and then we'll see one of the important analog to digital converters. Okay, so if I talk about DACs or digital to analog converter, they are mostly of three types. The first is register string. Okay, second is n-bit binary weighted register, or sometime it is known as binary weighted register. Okay, and third is R2R ladder. Okay, let us see what is register string kind of structure. So this is a typical example of a register string configuration of digital to analog converter or DAC. Okay, if you see, it shows 3-bit register string DAC. Okay, in this you have various switches, various registers. There is a buffer kind of comparator. Okay, and you have these bits as LSBs and MSBs. Okay, so this is known as a register string, and that's why it has derived its name as register string. Okay, these are the switches that I was talking about: switch 1, switch 2, switch 3 and switch 4. Okay, similarly these are also switches. In fact, this is also one of the switch. All right, so these are the switches, these are the switches, this is another switch. Okay, and this is the last stage switch. Okay, and then you have a op-amp acting as a buffer. Okay, now if you see, you have a reference voltage applied, and depending on where the switch is connected, okay, you have different connections, and based on that you have LSB and MSB generated, which is the input of your buffer. Okay, however, this kind of device or this kind of converters are impractical for converting more number of bits, because if you increase the number of bits, your register string is going to increase like anything. Okay, so let us see what are the advantages associated with this R string or register string kind of DACs. One of the greatest advantage of this R string kind of DAC is that it is very simple, and also if you use very less number of bit, okay, say 8 to 10 or even lesser, it is actually faster than others. Okay, then these kind of devices are monotonic, okay, and compatible with purely digital technologies. Okay, however, if you see, 2 to the power b number of registers and 2 to the power b number of switches is required for, say, number of bit is b. Okay, then similarly you need large area to accommodate all these registers. So if number of registers are very high, it also acquire lot of space. Okay, and in fact, if the number of registers are increasing, which is happening because of number of bits are increasing, okay, the settling time of this kind of configuration is also very high. Okay, so mostly string kind of structure are used for where less number of bits are required. Okay, then there is a R2R ladder kind of structure or R2R DACs. You can see reference DAC structure where this value is the MSB and VA is the MSB. The output voltage, if you, we have seen the op-amp working as a simple feedback structure or through when I am giving input through this inverting terminal. Okay, if you calculate this V out, it will come out to be VA plus 2VB plus 4VC plus 8VD. Okay, that you can do by using Thevenin's theorem or say even Kirchhoff's current law and Kirchhoff's voltage law. Okay, if you find this V out is coming to be this. Okay, so by using this simple structure which is known as R2R ladder, because I am using R here and 2R here. Similarly, in the another branch also I am using the same R2R configuration, and in the next stage also I have the same configuration. So R2R, and that's why this name is R2R ladder. Okay, and this is the output of this kind of configuration. You can increase the number of bits by increasing one more R2R structure. Okay, then another configuration that we have is n-bit binary weighted resistance DACs. Okay, this is one of the example where these are switches and these are binary weighted registers, where this is R, then 2 to the power 1R, 2 to the power 2R and so on. Okay, and at the end you have 2 to the power n minus 1 into R. Okay, and here your op-amp is connected through output by a feedback resistance R1. Okay, and this is the output voltage and ER is the reference voltage. Okay, so you have number of switches, so there are n number of switches, one for every bit. So this S0 to SN1 are switches. Okay, Then you have, since this is a resistive network, you have n number of resistors. One resistor is connected in the input circuit of each bit. Okay, the resistances are weighted, means if the resistance in the circuit for MSB is R, the resistance in the circuit for the next significant bit is 2R, and similarly you have seen that you have 2 to the power 2R, and similarly you have 2 to the power 3R, 2 to the power 4R, and similarly you have 2 to the power n minus 1 R. Okay. Now you have a reference source where ER in the form of ER. Okay. This reference voltage should be very stable in case of this kind of DSCs. Okay. You also have a current to voltage converter, which is basically derived by using a op amp that you have seen. Okay. This op amp adds up the current flowing in the resistive network to develop an output analog voltage signal, which is actually proportional to the digital input signal. Okay, fine. So let us see this with one example. Say suppose switch Sn-1, this Sn-1 switch, okay, is connected to the positive end of the reference source, and rest of the switches are grounded. Okay, under this condition only MSB is 1 and rests are 0. Okay. Therefore, the output voltage E0 should be equal to ER by 2, okay, for proper digital to analog conversion. Okay. In that case, E0 by ER will be equal to RF by R, where RF was the feedback resistance. Okay. Now, since E0 by ER is already 1 by 2, we can write that RF by R is equal to 1 by 2. Okay. So, resistance in the feedback circuit of the op amp is now this value. Okay. Now suppose for a binary input MSB is equal to 1, and also the next significant figure is also 1 with rest value equal to 0. Under that condition, E0 will be equal to 1 by 2 plus another 1 by 2 into 1 by 2, or 1 by 2 plus 1 by 2 square into ER, right? In that case, E0 will be equal to 1 by 2 plus 1 by 4, or 0.75 into ER. Okay. Now suppose R1 is the resistance in the circuit of bit next MSB. Input resistance for the op amp can be simply calculated as R into R1 by R plus R1. Okay. And E0 and ER are already known. Okay. So RF by R1 is given as 0.75, and R by 2RI can be given as 0.75. Okay. So by this, Ri can be given as R by 1.5, or since Ri is already R by R into R1 by R plus R1, as you have seen over here, you can compare this and you can calculate the value of R1 in terms of R. Okay. So fine, you can also understand this in terms of current. Okay. So from this figure, it is clear that if proper digital to analog conversion has to be carried out, the resistive network should be weighted. Okay. So you should have R, 2R, 2 to the power 2R, and so on. Similarly, the current values will be I by 2, and so on, right? So I0, the output current, can be written as I plus I by 2 plus I by 4 and so on, and I by 2 to the power n minus 1. If you resolve this value, you will get that I0 is equal to ER by R into 1 plus 1 by 2 plus 1 by 4 and so on, plus 1 by 2 to the power n minus 1. Okay. This is true only if all the bits are 1. Okay. So you can write a generalized expression for this, and in that you can write this I0 is equal to ER by R plus into dn minus 1 plus dn minus 2 by 2 plus dn minus 3 by 4 and so on, with d1 by 2n minus 2 plus d0 by 2n minus 1. Okay. So the output current is maximum when all bits are 1, that case we have just seen. Okay. So maximum output current in that case will be I max is equal to ER by 2 to the power n minus 2 by into R into 2 to the power n minus 1. So this will be the maximum output current when actually all the bits are 0. Okay. So this is the basics of DACs. Okay. You can read about it in more detail in a analog circuit course. Okay. Now let us see analog to digital converters. Okay. analog to digital converters are not as simple as the DACs that we have seen. Okay, they are actually complex in nature. Okay, so a number of methods has been used or has been proposed for efficient analog to digital conversion, and mostly these methods are classified under 4 heads. The first is successive approximation method, which is also known as sometime potentiometric type. Then you have voltage to time conversion method, and it is also known as a ramp type. Then third is voltage to frequency conversion method, which is also known as integration type. And then you have a dual slope integration method. Okay. Now let us see, it is not possible to cover all this 1, 2, 3, 4 different types of ADCs, but what we will do is we will quickly see one of the example, which is, say, in this case I am taking an example of dual slope integration method. Okay. So the block diagram of a dual slope integration or a based AD converter is shown over here. Just you see the different parts of this ADC. You have an integrator, op-amp based integrator. You know the output of an integrator, which is minus 1 by RC into, say, V into dt, right? We have seen this when we were discussing the op-amp. Okay, you have a comparator over here and a control logic. The output of this control logic is actually connected to a count, which can give you the digital output. This control logic is clocked. Okay, and you have a positive input voltage and a negative reference voltage, and this switch can move to and fro with this negative reference voltage and positive input voltage. Okay, and controller, this control logic is actually controlling this switch. Okay, so this switch cannot move without having input from a control logic. Okay, now the reference voltage and input analog voltage are sequentially connected to the integrator with the help of this switch. Okay, the reference voltage, which is of course at negative potential, okay, and the input analog voltage must be of opposite polarity. Mostly we take like this, the input voltage as positive, EI is positive, and this reference voltage as negative. Okay, the input voltage is integrated for a fixed input sample time. Okay, the integrated value is then discharged at a fixed rate, and time to do this is measured by a counter. You can see this counter placed over here. Okay, 2 types of command are given by the control to the counter. These commands are either the reset command or a convert command. Okay, so let us see when to give a reset command and when to see a convert command. Okay, so when a convert command is received by the counter, it automatically resets to all zeros and the switch connects the input voltage to the integrator. Okay, so the output from the comparator is designed such that at this time it will permit the counter to count up for a output from the integrator with the steadily increasing in its value. Okay, so the integration value that we have seen, minus 1 by RC integration of V into dt, this value slightly increases. Okay, on the next count, after the converter has counted all the way to the maximum value, okay, the switch changes its position. Now the input voltage is disconnected and the switch is connected to the negative reference voltage. Okay, so the switch connects the negative reference voltage to the integrator in this case. Okay, therefore now the integrator not only integrates the opposite polarity voltages, but it also ramp up the output voltage towards 0. Okay, meanwhile the counter is counting up from 0 once again. Okay, when the output of the integrator goes to 0, it causes the comparator to switch its output. Therefore, it stops the counter by the control logic. So the control logic gives the logic signal that it should stop counting. Okay, the binary number in the counter at this time is proportional to the amount of the time that it took the integrator to integrate down from its starting point to 0 value. Okay, so you can see this curve, okay, we'll see that this integrator output rises from this convert command, okay, to a value T1, which counts up to the this value is up to the reference voltage, okay, and then this T2 represent counts up to the input voltage, okay. Therefore, the binary count is actually proportional to the input voltage, okay. This figure here illustrates the output from the integrator during a conversion cycle. The difference in the slope of this curve is due to difference in voltage level of input voltage EI and the negative reference voltage ER, okay. Say suppose T1 is the count when the input voltage is applied and T2 is the count when the reference voltage is applied. The ratio of input voltage to reference voltage is equal to T2 by T1, okay, or EI can be given as T2 by T1 into ER, okay. Similarly, you have other kind of ADCs like successive approximation, voltage to time conversion and voltage to frequency conversion. Of course, discussing all these types of ADCs is beyond the scope of this course, and if you are interested, you can learn this through a basic analog circuit book, okay. Then for some of the sensors which are mostly optoelectronic devices, you need light to voltage converters, okay. We have already seen charge to voltage converters when we were discussing the op-amp, okay. Sometime you need light to voltage converters, and light to voltage converters are based on combination of photosensors and current to voltage converter circuits, okay. For detecting extremely low intensity lights, typically one or several photons, I mean if you have that level of photon energy, okay, or photon packets, the photomultipliers are mostly used, okay. However, when you have abundance of light, or say for example in a NDIR gas sensor where you have a precise infrared source, okay, and you do not have very less number of photon packets, in that case a simple photosensors like a photodiode or a phototransistor or sometime even photoresistors for a cheap kind of device is more than sufficient, okay. So a photodiode, for example, can be represented by an equivalent circuit which is shown over here, okay, all right. So in that case the output voltage is actually can be given as IP into R, where this is the current IP flowing through this photodiode, okay. So similarly you can have other equivalent circuits for similarly for photoresistors as well as for phototransistors, okay. We'll take up the equivalent resistances of this photomultipliers and as well as this phototransistors wherever it is required. Particularly they will be very useful when we will discuss the occupancy sensors, okay. There we will discuss in more detail about the this light to voltage converters, okay. Apart from these basic circuits, we have other circuits available like for minimizing the noise, you have to, depending on what kind of noise, you have to give provision for noise mitigation or noise suppression, okay. Similarly, you can have circuits for EMI and EMC shielding for your device if your sensor's requirement is that, okay. Similarly, we have other requirements arising depending on our need for the sensor. So we will tackle all those interface circuit problem wherever this scenario arises, okay. So that is all about the module 4, where we have discussed the interface circuit of the microsensors and nanosensors. We will learn some of the examples of these sensors in coming weeks, okay, and we'll start that with a chemical and humidity sensor, okay. So thank you. We'll meet in module 5 with more details.